The last session. So I'm glad to introduce Avi Klein, who now works at Sandisk in California. He's a graduate of Technion, and at Sandisk he's in charge of studying flash capabilities versus market requirements, both today and tomorrow. Thank you.
Okay, good afternoon. I will try to make the connection between resistive RAM and the current flash industry. So we talked a lot about resistive RAM, different future applications. I will try to connect this to the mainstream of data storage, which is today represented by a NAND flash. I will talk about the NAND flash scaling limitations, the motivation, why we need to continue the cost reduction following Moore's law. I will review some of the emerging memory technologies, focus on resistive RAM, and also show the market applications. And I hope I will not disappoint you if I will talk about conventional in-the-box market applications and not out-of-the-box market applications. This is what we do. This is how we make our livings. And we are trying to bridge between today and the long future by looking at the near future. Okay? First of all, because I'm talking about the future, people say that it's very difficult to make predictions, especially about the future. I need to show this legal disclaimer that everything I say is just prediction and it's true for today. Okay, this is Gartner. Same applies for IDC, for Forward Insights, for any analyst that review our market. And we are here in 2012. Last year, we produced, the entire industry produced about 20 exabytes of flash memory for data storage. 20 exabytes. And the prediction is within 4 years to go to more than 130, 140 exabytes. And if we just convert the entire fabs in the world, not very many, few in South Korea, few in Japan, one is Singapore, and that is. No much more than that. 4 or 5 companies control this market. So even if we convert everything to 20 nanometer, sub 20 nanometer, 1X, 1Y, 1Z, even if we convert everything to 3 bit per cell, we might be somewhere here. And that means that in order to supply this demand, and let's assume that this demand is true. We are here in 2011. We are here. Sorry? Here. Here. Sorry. Let me click one more. Sorry. Yes. So we are today here. And let's say that if we make all the conversions, scaling down and so on, and 3 bit per cell, we might end up here. So in order to make the demand, the entire industry need to invest in another 5, 6, or 7 megafabs, which is more than $50 billion. And the question and this investment need to happen in the next 2 years, 3 years, in order to satisfy this demand. And the question is, what are we going to build these fabs for? What will be the equipment mix? Is this going to be floating gate NAND? Is this going to be resistive RAM? Is this going to be something else? Because when we build a fab, we build it for 20 years. And the equipment mix and the facilities and the chemistry and everything need to, it's pretty difficult to change it along the journey. So this is a connection to resistive RAM. We need today and next year and 2 years from now to understand the future of resistive RAM in order to make the right decisions. By the way, one more thing here. We see here the demand drivers, iPhone in 2005, tablets today, cloud 1 or 2 years from now. These are the conventional demand drivers that people know about and can make some kind of predictions. There are not demand drivers here which cannot be predicted because this is a disruptive demand and disruptive applications. So that's the reason I said I will talk about conventional demand. Looking at Moore's law, this is a cost curve of NAND. It's actually faster than Moore's law in the last 10 years, since the beginning of the decade. It's faster than Moore's law. It's slowing down because it's become more and more challenging to continue the scaling. We cannot necessarily double the density or reduce the cost by 50% every year, but still there is a way to go. And the title here is NAND scaling will extend as long as possible. I heard in the morning some numbers, doesn't mean that we're going to support it, but we will extend it as much as possible. And the question is, every technology that will be post-NAND for data storage need to fit here. It cannot be a technology that comes on this port or this port or this port. By the way, I on purpose show this and this and this because this is where PCM, phase change memory, and magnetic memory and other memories reside. If we want to have something which replace or continue the mainstream data storage flash, it needs to fit here. And this becomes very challenging. Every year, as we continue the cost curve, it's going to sub 50 cents per gigabyte, sub 40 cents per gigabyte, and so on. So every year that we continue, the replacement for NAND, like resistive RAM, has a very challenging starting point. So a technology that need to continue NAND need to have smallest cost per bit. I showed the number. Need to have a very high gigabit capacity per single die. So today, the largest die is 128 gigabit on a single die. This is MLC, 2 bit per cell. It was presented in IEEE 2 weeks ago, and it's less than 2 square centimeter. So in order for resistive RAM to continue this, it needs to have a very high capacity and also low form factor. It needs to be fab-friendly, scalable, reliable, and so on. And of course, once we invest in a fab, it also needs to generate some return on investment, which is not obvious when there is so much uncertainty about the continuation of the cost curve. And one thing which is known to all the NAND users, NAND is very unreliable. Actually, when people started to think about NAND 20, 22 years ago, nobody believed that it will be where it is today because the bare NAND has so many errors, so many issues, that only with a complete solution of controller plus flash management plus all the know-how, how to correct the errors, how to manage the block and the page and the data and wear leveling and all the little tricks that make flash usable, this is a trick that makes flash so successful. So the reason for flash to be so successful is not because it's good or perfect. The only reason, because it's cheap. And the motto, the theme of today, that money talks. And money talks for NAND, and money will talk for resistive RAM. And we can see here that there is an increasing gap between capabilities and requirements. And the requirements become more and more challenging because NAND is used in SSD. It's much closer to the CPU, to the operating system, to the host. It's basically start to work like a working memory in several of the requirements. And that means that this bridge, this gap, become more and more difficult. And I will show that we have some solutions how to close this gap. This is about the motivation. Something about NAND. People usually talk about 3 reasons for the difficulties to continue scalability. One of them is lithography. We all wait for the extreme UV, but until we get the extreme UV, even to continue the lithography scaling with existing 193 emergent lithography become more and more costly because we need to do double space, double patterning, and all kind of tricks, which make it very expensive, even with the existing lithography database. So lithography become more and more expensive, even if we can continue to do the cost curve. Physical limit, we can see here what we call cross-coupling, or the interferences between cell to cell. And number of electrons also become lower and lower, which create a signal-to-noise issue. So all these things make the NAND scaling very challenging. And if we look very closely to the NAND, this is 2 bit per cell. This is a distribution of threshold voltage for 2 bit per cell, which means 4 levels. The arrays is here. We can see all kind of factors that limit this VT window, a negative VT limitation, positive VT limitation, VT window limitation for the entire window, and so on. There are many factors that need to be considered when we look at the overall reliability and performance of a NAND. I will not go into all of it, but this deserves another discussion, because it's very interesting to see what kind of solutions the industry, not only Sandisk, but the industry can develop in order to make this scalability continue to sub 20 nanometer, 1X, 1Y, 1Z, and so on. And of course, here is an example of some of the solutions. Every technology, we think that we cannot continue. This is just the endurance target. You know, the data flash need to be write and erased many, many times. So this is the endurance target. There is a natural drift because of the reasons that I mentioned, and we find ways to solve it. Every generation, we found 1 or 2 tricks, both on a system level, physics, device, cell design, architecture, and so on. And of course, we cannot say anything about NAND without a system. The system become more and more sophisticated, the flash management. It started with very simple system. Today, we talk about application involved in the ways that NAND is managed and operated. And in the future, we're going to talk about state-aware. As we know, NAND is used in the mobile applications without power connected or with battery connected. And it's very important to do the right trade-offs between performance, power, data retention, endurance, and so on. So by knowing the application and knowing the state awareness, we can optimize the NAND along the usage. Something about emerging memories. So this line is the write program cycles. And this is the capacity. And we have here 3 groups. This is a working memory. This is the code storage. And this is the data storage. Our NAND is in data storage, means that it has very high capacity, very low cost, very low power, but very little endurance cycles compared to working memory. Working memory need to have very fast switching speed and very fast and many, many endurance cycles. And code storage is also a data storage that work in this regime and not here. So the candidates to replace floating gate NAND are resistive RAM, BICS, which is a 3D NAND. It's another version. but it's based on electrons, charge, and of course HDD. So everything we heard today, phase change memory, and magnetic RAM, and so on, they don't belong to the discussion of data storage. We saw different versions of this chart today. I will not speak too much about it. Just showing the materials used for resistive RAM, we can see that a lot of materials from the periodic tables can have a switchable properties. Of course, what is important to find the right Gibbs energy and to right properties that make it commercial and also suitable for large memory array. Here we can see just for the binary metal, we can see all kinds of research activities. This is just a small part of it. And of course, we can see here a full list of materials. This just shows how complicated, how, let's say, not focused research in Korea, in Taiwan, in IMEC, in universities in California. Everybody chooses his own material, oxide, hafnium, zirconium, and we know that there are differences. But what will win is very difficult to predict, and what are the properties that needed to make it a mass production is also very difficult to predict. And this is really the key of what I want to talk now. So this is by Professor Wasser. Yes, he put some of the properties that required for resistive RAM to replace data storage. And of course, some things are not mentioned here, but when we deal with the future of resistive RAM, we also add other parameters to see what is the prospect, the potential of resistive RAM. We, for example, look at current scaling. Current scaling is very important because maybe something can work okay for 30 nanometer, 40 nanometer. We want to make sure that the power, current, energy will continue to scale also for 10 nanometer and sub 10 nanometer. Also, not everything that was proven on a 1 cell or 1,000 cell or 10,000 cell will work for 128 gigabit die, which is 128 billion bits on less than 2 square centimeters that all need to work in harmony. So the uniformity, everything we know about statistical process control, min plus 3 sigma, how to control the thickness, and everything we knew from the classical studies become not very trivial when we look at 128 millions of memory cells that need to be orchestrated in harmony. So proving resistive RAM on a small scale doesn't mean that it will be successful on a large scale when we need to control the capacitance and the power and the currents and so on. Of course, there are other options. I will not go into it. But PCM, I think it was a consensus here that in the near future, PCM can be cost competitive with NOR. It can be some kind of solution if it can replace NOR and DRAM together for PARSH, but it's not, there is no cost projection for PCM to replace NAND as data storage. Same for STT-MRAM. Go quickly on this. It doesn't have the cost potential as NAND. Large cell size, no MLC, no 3D. So it can be excellent properties in terms of endurance, reliability, space, military, reliability, all kinds of features, but just as replacing NAND and continuing this 140 exabyte of the market requirement is probably it will not happen with this in the near future. Okay, so what we focus, and I think that Yaakov also mentioned it, we focus on a cross-point memory, which is a 3D resistive RAM. So it's the same resistive RAM that was discussed here with built also in layers on top of each other. And also 3D NAND, which is not in the scope of our talk today, but this is another option that we discuss. And now let's look at the application trends. This is the memory hierarchy of the computer architecture. We can see here the flash drive, and this is the place where a NAND flash usually stays. And as I said, since money talks, there is a prediction that because of the low cost of NAND compared to DRAM, compared to HDD, compared to all other memory components, flash in the future can erode some of the DRAM, not because it's better than DRAM, just because it's 10 to 20 times cheaper than DRAM. And this creates a motivation to think about solutions. And of course, it's already started to erode part of the HDD by doing SSDs. And this is the difference from Gartner. This is the difference between DRAM and NAND, just showing the driving force, the motivation to look at other ways to use NAND in the future. And when I say NAND, I also mean resistive RAM. So if resistive RAM continues the cost curve of NAND, everything I said about NAND is true for resistive RAM. This is a cloud. And today in the cloud, we have at the first node and at the last node, we have flash memory. And flash memory actually enabled a new level of performance and user experience and usage for both at the data centers and at the handheld applications. If we look at the last node, this is extreme mobility with the mobile phones, tablets, and these are the data centers which require very fast response time. And what is required from NAND, from SSD, is high performance, high reliability, small footprint, low power, low total cost of ownership. HDD today and DRAM today cannot give all these features, especially when energy becomes so critical in data centers and people look at ways to reduce energy. So for example, DRAM need to refresh every 64 milliseconds, a lot of energy. In last ISCC 2 weeks ago, energy was a theme of the conference. So talking about NVM, it's create new potential to save energy because you don't need so much refresh. Of course, when we look about different type of usages, on the enterprise SSD, we have write-intensive application, mixed use, and read-intensive. So for example, high-performance computing and database logging are related to write-intensive. Read-intensive is indexing, web servers. Here we have email. Each of them require different specification of endurance, performance, and so on. And we need to make sure that our products, whether it's flash or resistive RAM, are suitable for this variety of applications. If we look at this chart, this is a mobile phone, tiny device with many, many type of usages. This is the IOX, which is a measure of performance. And this is the chunk base, or what kind of, what is the size of the data that we need to manage, manipulate during operation. And here we have all kinds of applications that are being used by a typical user. So web browsing require about 150 IOPS, and it's a random performance. Video recording is a sequential performance. So random means very small chunks of data. Sequential means very large chunk of data. And with this single flash, just this tiny USB flash that is in a mobile phone, we need to make sure that it's tuned and optimized for all this type of application. And it's a very hard work. It requires a lot of know-how of the flash people, the system, the controller, deep understanding of how the phone companies or the tablets companies are using it, deep understanding of how the end user is using it, in order to make sure that the user in order to make sure that the user experience is satisfying. Now let's look about how resistive RAM is fit into this story. So today's NAND is represented by this curve. We can see here a few of the requirements. This is a low cost per bit. This is endurance, program array cycles. This is random read-write, sequential read-write, and also low energy, low power. And this is data retention. So this is NAND. As I said, it's require a lot of system solutions in order to be useful and accepted by the type of usage. Now, if we look at BICS, it's not the topic today, but it's very similar to NAND. And when we go to resistive RAM shows promise on low cost per bit. So once it materializes and become commercial, there are still challenges in order to make it successful. Still challenges, as some of it we mentioned today, some of it need to read the papers to understand. But it has a potential to have low cost per bit, more than NAND. Because we call it RAM, random access memory, it's trivial to say that it has higher endurance than NAND. It has higher random read-write than NAND. Sequential is not necessarily, because it's RAM, it's not a type of a NAND still with a large block size is better. And it can have a long data retention. So what we can see that on the most important parameters, requirements from resistive RAM is show promise, and therefore it's believed to be extending the cost curve of NAND. Still, not all these parameters were demonstrated simultaneously on the same device. And it was not demonstrated a large-scale integration. And still, current and power is an issue. But the amount of activities, the amount of research going into this make it something which is a focus of the industry. And therefore, this conference in Israel is very relevant to this type of discussion. And the summary from technology, NAND flash scaling will extend as long as possible. And as I said, there are all kinds of solutions, innovation, creativity that can make another trick to go another generation. Still, cost reduction may slow down a bit, but we will try to extend it. Flash can penetrate into HDD storage and DRAM segment just because it's much cheaper. On the DRAM part is because it's cheaper. On the HDD, because it has better features. 3D resistive RAM has the potential to continue the cost curve. Resistive memory refers to many types of materials and switching mechanism, and I think it was very clear today. And the capabilities of resistive RAM make it suitable for various applications. I mention now only the conventional applications, cloud, computing, mobiles, tablets, and so on. Of course, because of what we saw in the previous slide, there are so many new applications that some of them were mentioned today that are not included in this talk, but when we have a memory which is very cheap, with such a good endurance and performance and so on, there will probably be a new type of innovative applications that I didn't mention here. And regarding applications, in the cloud ecosystem and also in the mobile handheld device, the flash and the post-NAND actually enable new type of form factors. So in MacBook Air and Ultra, HDD cannot go anymore. It can create very thin device, very energy efficient device, and by this the user experience become much more satisfying compared to HDD and then other type of memories. And I think by this I finished.
Questions? Thank you very much.
Okay.